Okay, we're going to start here our Chapter 9 notes here. This is our last chapter in probability. It's kind of like a segue chapter between probability and inference. And we're going to be taking a look at this idea of sampling distributions. It says in the purpose of the chapter is to prepare for the study of statistical inference by looking at the probability of sample proportions and sample means. Key phrase there, we're looking at two different things. Sample proportions, which is looking at categorical variables, and sample means, which is looking at quantitative variables. And what we really want to know is how likely is it that our sample proportions, or sample means, are close to the actual proportion and actual mean. Because isn't that the idea? The idea is to when we collect these samples, we want them to tell us something about the true means and the true proportions. Because otherwise, why are we doing this? Before we can really get into that, we have to clarify a couple of things. We need to talk about the difference between a parameter and a statistic. And as we look at a parameter, it's a number that describes the population. Parameter, population. Statistic, well, that goes with a sample. Now, why is that important? Because, well, first of all, they have different notations that we'll look at in just a second. But also, it just gives us a better understanding of what we're actually doing. When someone gives you a value, you want to know, or you need to know, if that's coming from a sample or a population, so that you can then use it to decide whether it is valid or not and what you can do with that value. Let's look at a quick example here to make sure we are clear on the difference. It says the current population survey of 146 households states that the average income is $60,528. Our job is to determine if this is a parameter or a statistic. Well, if we think about that, parameter goes with the population and the statistic goes with the sample. If we look at this survey, it's only of 113,000 households. And we need to determine, is that a legitimate value for the whole population, or is it less than that? Clearly, if you think about it, there are over 300 million people who live in this country. So if that were to be representative of the population, well, then there would be a heck of a lot of people living in each household, and that's not the case. So this particular data point here is a statistic, because it's not representative of the whole population. Now that we're clear on what they are, we want to look at the notations that go with each. If you think about means, you've seen both of these symbols before. If you're talking about the mean of a population, you're talking about mu. And you should therefore be able to recall what the mean of a sample is, x bar. When you're talking about a proportion, it shouldn't surprise you that when you're talking about the population proportion, that's just p. But when you're talking about the proportion of a sample, we refer to that as p hat. P with the hat over it. And that might recall you back to when we talked about linear regression, where we talked about y hat. The y hat was just an estimator of the true value of y, just like the p hat is an estimator of the true value of p. All right? Parameters are fixed while statistics vary, because as you take different samples within a population, you're going to have different means. You're going to have different p hats. The sampling variability is the value of a statistic varies in repeated random sampling. Well, we just discussed that. But the goal is to hopefully have x bar tell us something about mu, or p hat tell us something about p, so that we can use that to make decisions in our analysis. Take a minute to look at these two, pause the video, and make sure that you can determine which ones of these are parameters and statistics. And as it says, use the appropriate notation to describe that value. So pause, and then hit play when you think you have it. The first one says, do you believe in ghosts? In a Gallup poll, 160 out of 515 U.S. adults answered yes. Well, first of all, 515 U.S. adults, clearly that's not the whole population, so this is a sample. So they want us to state whether it's a parameter or a statistic. Sample goes with statistic. But they also want us to use the proper notation. And as we look at this, you either, if you're answering this question, you're either answering yes or no. making this a categorical variable. Therefore, this is a proportion problem, so we'll use the notation p hat. And p hat equals 160 out of 515. If you look at the second one, the average height of 8th grader boys is 65 inches. Well, it doesn't say the average height of 20 8th grade boys or 300 8th grade boys, so we're going to assume that this is the entire population. Population is an estimate, a parameter is an estimator of the population, so this is a parameter. If we're talking about someone's average height, that's a quantitative value, so that's going to be a mean that we're referring to here, not a proportion. And since it's a parameter, we're going to use mu, and in this case, mu equals 65 inches. Okay, pretty clear with that, just some basic review. Now, if we were to take many samples, what would happen? If we were to take a large number of samples from the same population, would they all look the same? No, not exactly, but they should be pretty close, as long as we don't have any bias or anything else wrong with the way that we collect our data. What we would do is we would collect an X-bar or a p-hat for each of our samples, as you've done before, but in this case we're going to take a whole bunch of these samples and put them together. Then we would make a histogram of those values of either X-bar or p-hat, and we would look to determine the shape, the center, and the spread. And at this point you might want to make a conjecture about what that would look like. Do you think it would be skewed one way or the other? Do you think that it would be roughly symmetric or maybe even approximately normal? What about the center? Is it going to be close to the true population, mean, or proportion? How about the spread? Is it going to be very widely spread? Does the spread change based on how large our sample is? Well, if we were to actually do this in real life, well, that would be too expensive. That would take too much time, too much resources for us to actually do. But what we can do is we can simulate this sampling distribution using simulation, using probability, what we know. If we look at this example here, if we were to do this in class, we would have everybody take a whole bunch of different we would take a whole bunch of samples and we would look at the data together. But I'll go ahead and simulate here for you here. It says in this example, customs officials at Guadalajara Airport want to be sure that passengers do not bring illegal items into the country. Since they do not have time to check every passenger, they require each person to press a button, which will either display a green light or a red light. Obviously, you could imagine that a red light would represent a passenger that requires search. Green light means you just go through. And customs officials say that the probability that the light will turn green is 0.7. So we could say the probability of green equals 0.7. Okay? And we're going to simulate this. We're going to simulate this. I'm going to do it myself using the rand_int function. We're going to say 1 through 7 represents a green, and 8 through 10 represents a red. I'm going to run 10 simulations, and we'll look at what that would look like on the board in just a second here. So if I'm doing rand_int, the three numbers you're entering with rand_int are the low, the high, and the number of numbers. I'm just going to take numbers one at a time here, and the first number that I come up with is an 8. Now if I look at how I assign my digits, 1 through 7 was a green, 8 through 10 was a red. Clearly that tells me that this one is a red. All I have to do is hit enter, and I'll get my next value there. It's a 10. That's a green, so that person got through. And I'm just going to go a little quicker here. 3, 4, 1, 10, 2, 1, 6, 1 more, and 9. And as I go through, whoops, hopefully you caught that. I messed up there. The second value is actually another red. And then we had 3 greens in a row. And we had a 10, which was a red, green, 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 and then finally the last person got stopped as well. So if I look at my simulation here of 10 people going through this security checkpoint here, my p hat would be equal to point, how many greens did I have? 1, 2, 3, 4, 5, 6. I had 0.6 as my proportion of greens, or my proportion of people who got through here. Okay? Now, if we were to look at this and put all of them together, well, we would see something pretty interesting here. But before we get to that, let's make sure we're clear on a couple of different things here. First, it says, what's the population proportion? And I even gave you a hint there that I'm looking for P. Okay? P, which in this case means the proportion of observations that are going to be green for the whole population, should be 0.7. What's our sample proportion? Our p hat. Okay? Our p hat that I got was 0.6. Is that close? Well, sure, it's pretty close. And if we were to take this opportunity to do something like this in class, which we might do in class in a day or two, this would be something that would end up being pretty close to the true population proportion of 0.7. And if we repeated this simulation many times, what we would see is that the p hat that we got, that would approach P. It would get closer and closer as our samples got, as we repeated this sample many, many times. Okay? And if we would look at this histogram here, this would show us what would look like if we had 1,000 SRSs, 1,000 simple random samples of size 10. And this is the approximate sampling distribution, okay, for p hat. Couple things here. First of all, we have this phrase now, sampling distribution. It's bolded, it's underlined. That's a pretty important thing. The sampling distribution is all possible samples of size n on this distribution. Okay? Now it says it approximates it because it's only 1,000. Clearly there are going to be a lot more than 1,000 possible samples for any population of any real size there. Now if we were to look at it, what about the shape? Does it appear that it's roughly symmetric? Yeah, pretty roughly symmetric. In fact, it's probably close to normal as well. How about its center? Not surprisingly, it's centered there at 0.7. And as far as the spread, well, it looks like it goes down to as low as 0.58 and as high as 0.82. Okay, with the true mean being centered there at 0.7. Well, first of all, it's relatively centered around that point. But it also is not that far. We could be as low as 12 percentage points below or 12 percentage points above. And what we'll see is that when you increase the sample size, not increase the number of samples, but increase the sample size, that standard deviation or that range, that variability, will get smaller and smaller. Okay? And that's exactly what we see right here in this example. But before we get to the example, let's formalize this definition. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size in the same population. That is something that, if I were you, I would start in your notes and say that's pretty much guaranteed to be a test question at some point. We don't do a lot of definition questions, but that is one that's really important for this entire chapter, so I would expect to see that at some point. Okay? Now, if we were to look at this example on the bottom, it says, consider the process of taking an SRS of size 2 from the population of table B, the random digits table, and computing the X bar of the sample. Now, if you think about that, we're taking an SRS of size 2 from the population there, okay? We could perform a simulation, but in this case, we can construct the actual sampling distribution because we know what the possible outcomes are. We know that the first digit and the second digit can take any number from 0 to 9, and we know that they're all equally likely. So we could estimate the mean, the X bar, of that simply by looking at all the possible outcomes there. And if we were to look at it, well, not surprisingly, it's centered at here 4.5. Okay? Because, well, if we go from 0 to 9, the midway point there is 4.5. Same thing with the other side is 4.5. And there's a lot of different ways that you can get to values at 4.5 there. All right. Now this is the end of the first part of this section. These are going to be the exercises we work on in class the next day, tomorrow. All right. So make sure that you understood everything that we did in here, and we'll come back with the next video very soon. Have a good day.